Anuskan will discuss about those things later. It's yet to be discussed, okay? So we take the help of a theorem and we try to locate them. If body 1 is moving, okay? Are you getting my point? So everyone understood this, right? How to locate an instantaneous center. So you choose any 2 points, you draw velocity vectors, draw perpendiculars to the velocity vectors. Wherever the perpendiculars meet, that is your I center, okay? That is your I center. Since I am saying this is center of rotation, we can define angular velocity, omega. So since the body is rotating about this center, velocity of any point on the body is directly proportional to its distance from center of rotation. You can write like this. Velocity is r times omega. Different points, radius is different. Okay. And I am writing this is I12 or 21 because just to show this is the instantaneous center of rotation for bodies 1 and 2, where body 1 is fixed body, that is board, and body 2 is the body moving. Okay. So there's no difference between I12 or I21. Let's write down like this. Instantaneous center. Let's write down like this. It's not a true center. It's not a true center. Instantaneous center of rotation. It's not a true center. It is also called as a virtual center. Instantaneous center of rotation. It's also called as a virtual center. Okay. It's also called as virtual center. It's also called as virtual center. Next, write down like this. As the link changes its position. As the link changes its position. As the link changes its position, its instantaneous center of rotation changes. As the link changes its position, its instantaneous center of rotation changes. As the link changes its position, its instantaneous center of rotation changes. Its instantaneous center of rotation changes. Its instantaneous center of rotation changes. Next one. Locus of all the instantaneous centers. Locus of all the instantaneous centers is called as Centrode. Locus of all the instantaneous centers is called as Centrode. Locus of all the instantaneous centers is called as Centrode. Locus of all the instantaneous centers is called as Centrode. Next one. Locus of all the, this is instantaneous center. As the link is changing its position, instantaneous centers are changing, right? Locus of all instantaneous centers, we call it as centroid. You will get a curve, okay? So this is instantaneous center. You can see this axis perpendicular to the board. This is called as instantaneous axis, okay? This is called as instantaneous axis. Next item. Locus of all the instantaneous axis is called as Axode. Locus of all the instantaneous axis is called as Axode. Locus of all the instantaneous centers is called as Centroid. Locus of all the instantaneous axis is called as Axode. Axode. Okay. This is all about I center. So it's not the case every time you will get the velocity vectors oriented in different directions. Sometimes you may encounter a case where the velocity vectors are parallel, okay? This is one case, okay, where the velocity vectors are non-parallel. Next, write down like this. Case 2. Velocity vectors are parallel. If velocity vectors are parallel, how to locate I center? If velocity vectors are parallel, how to locate I center? So whenever velocity vectors are parallel, it means the body is either in pure rotation about a point or it's in pure translation, okay? So you may encounter these two kind of cases. Taking this body. So I'm choosing 2 points like this, A and B. So if you draw the velocity vectors, so here the velocity vector is in this direction. So here also velocity vector is in the same direction, but of higher magnitude. This is VA, velocity vector at point A. So this is velocity vector at point B. Okay. So what you do is, whenever 2 velocity vectors are parallel, you draw a line passing through tail of the vectors. Draw a line passing through tail of the vectors. And similarly, you draw a line passing through head of the vectors. So wherever the 2 vectors meet, that is instantaneous center of rotation. At this instant, it is rotating about this point. So velocity is directly proportional to displacement, okay? So velocity of this point is r times omega. This is the velocity. Velocity of this point is r times omega. So since radius is more, velocity is more. But omega is same for both the points. So otherwise you may encounter a case something like this. This is velocity of point A, this is point A. And for point B, you may encounter a case like this. Velocity of point B is in this direction, this is B. Here also the same thing. You draw a line passing through tail of the vectors, and then you draw a line passing through tail of the vectors. Head of the vectors, sorry. So wherever the two perpendiculars meet, wherever the two lines meet, that is the instantaneous center. It is the instantaneous center. Like we don't draw a straight line here. This is I-center. So if two velocity vectors are parallel, you may encounter a case like this. So here in this case, if the two velocity vectors are of same length, then these two lines will never intersect, okay? So that we say I-center lies at infinite. It's in pure translation. Okay? This is I-center. So I say the body is rotating like this. Here the body is rotating about that point. Sorry. Okay. You understood how to locate an instantaneous center, right? Yeah, for a single link. So I have not yet discussed for multiple links and so on. So when a fixed link is given, when a moving link is given, you can look at I-center, right? So between a fixed link and a moving link, you can look at the I-center. So this is the procedure for locating the I-center, okay? Yeah. Just listen here. Whenever I say instantaneous center of rotation for two bodies, just look here. What exactly it means? So I'm taking a disk. These are the properties of center, okay? So I'm taking a disk. The disk is hinged here, okay? So what I did is I fixed a nail here. On the nail I mounted a disk and the disk is rotating, okay? Now the disk is rotating about a fixed center. For this disk, the center of rotation is this one. This is center of rotation for the disk. That is center of rotation for the disk. The disk is rotating, so body is in one plane, and above the board, so I have this disk. This disk is spinning, okay? This disk is rotating. Now see here, you take any point on the disk. I can say this point on the disk. So if you look at this point on the disk, and you see the coincident point on the board. So I can say this point on the disk is moving, whereas the coincident point on the disk is stationary. I can say you take any point on the disk, every point on the disk will have some relative velocity with respect to its coincident point. Yes or no? So all the points on the disk are moving when I rotate this disk. When I rotate this disk, all the points on the disk are moving, and all the points on the disk are having relative velocities with respect to their coincident points, except one point. So what is that point? So I can say if you look at velocity of center of the disk, so velocity of center of the disk is 0, and if you see the coincident point on the board, velocity of coincident point on the board is also 0. Coincident point in the sense, if this is the disk, so I'm saying this is the point on the disk. So just below this point on the disk, you can imagine one more point on the board. So velocity of this point, this point is moving, but the coincident point, whenever there is a coincident point, you take any point on body 1, so just behind body 1, so you will be having one more point on body 2. It's a coincident point, okay? You take any point on the disk, all the points on the disk will have relative velocity with respect to their coincident points, except center, okay? If you see velocity of center of the disk, velocity of any point is r times omega, right? R times omega. Velocity of this point is r times omega. Velocity of this point is r times omega. Velocity of center is 0, okay? Because r is 0. Velocity of center of disk is 0. If you see the coincident point, that velocity is also 0. Whenever I say center of rotation between two bodies, center of rotation between two bodies is nothing but it is a coincident point where there is no relative velocity, okay? Now see here, if I say this board, if this entire board is moving in this direction with a velocity of 2 meters per second, so I can say the center will also have the same velocity 2 meters per second, okay? The center will also have 2 meters per second. So I can say only the center will have 2 meters per second. All other points will have different velocities. I can say this point on the disk, velocity of this point on the disk is 2 meters per second. So velocity of coincident point on the board is also 2 meters per second. Whenever I say center of rotation, so velocity of that point will be same, okay? Whether you consider on body 1 or body 2. So here I am saying for the disk, if this is center of rotation for the disk, velocity of this point on the disk will be same as that of velocity of the coincident point on the board. What is velocity of this point on the disk? 0. What is the velocity of coincident point of this point on the board? That is also 0. What is velocity of this point on the disk? R omega. Velocity of the coincident point is 0. Are you getting my point? Whenever I say center, if I say this is the instantaneous center for board and the disk, velocity of this point should be same. That is center. So here also the same thing. So I am saying that at this instant, if you stand here, you can see the motion of this body to be in perfect rotation with respect to the board. There is some relative motion with respect to this body and the board. This relative motion can be seen to be in perfect rotation by standing at this point. I am saying that at this instant, this point is the center of rotation. This point is center of rotation. And I told you that the center of rotation can lie anywhere. So the center of rotation lies wherever the two perpendiculars intersect. And where the two perpendiculars intersect depends upon the orientation of velocity vectors. The two perpendiculars may intersect on this body also, or they may intersect on the board, or they may intersect outside the board. But wherever they intersect, velocity of this point, if I consider on this body, velocity of this point, if I consider on the board, it should have same velocity. Now see here, what is shape of this body? Shape of this body is something like this, right? Shape of this body is something like this. If I assume the shape of the body is not like this, everything is same. The body is moving exactly in the same way, but the shape of the body is not like this. If I assume shape of the body is something like this, if I say the shape of the body is not like that, the shape of the body is like this. The shape of the body is like this. I can say if I extend that body, I can make eye center fall on that body. Or what did I do is, so that this was the original body, this is the body, this is the body. For this body what I did is, I welded some extra portion like this. I welded this extra portion. If I weld this extra portion to the existing body, this body is moving, the welded part also moves, and this point, now it lies on the body. If it lies on the body, now the shape of the body, when you weld it, so the shape of the body will be this. Entire thing is the same body. This is the body. And eye center is now falling on the body. So now I can say like this, if I say this is center of rotation for the board and this body, then I can say like this, there are infinite number of points on this body. All the points on this body will have relative velocity with respect to their coincident points on the board. Except this point. Except this point. This point, if I consider this point on the body, velocity of that point, it will be exactly same as velocity of the coincident point on the board. So what is velocity of its coincident point on the board? 0. So velocity of this point will also be 0 at this instant. If the board is moving with some velocity, I can say this point will also have the same velocity. Are you getting my point? Whenever I say this is instantaneous center of body 2 with respect to body 1, or body 1 with respect to body 2, it means that, so this particular point has the same velocity whether you consider on body 1 or body 2. Okay? So between these two bodies, there will be only one point where you don't have relative motion, that's instantaneous center of rotation. So yes or no? So I told velocity of body B is r times omega. So if you find out velocity of any point, if I say velocity of this point, r times omega, velocity of this point, r times omega, velocity of this point, r is 0, right? Its velocity is 0. And velocity of the body is also 0. So whenever I say the common instantaneous center for two bodies, so there should not be any relative velocity, okay, between the two coincident points at that eye center. Are you getting my point? What is eye center? Eye center, so physically it is, you understood, you draw two perpendicular velocity vectors, you draw two perpendiculars, wherever they intersect, that is your eye center, that's okay. And if you stand there, you can visualize that to be in perfect rotation, that's also okay. So it has other properties. So this is one important property which we use for solving most of the problems. Okay, whenever I say instantaneous center of two bodies, so at that point, so the two bodies will have same velocity. Or in other ways, at that point, there will be no relative velocity between the 2 points. Just write down like this. Just write down like this. Write down this point like this. Write down like this. Instantaneous center of body 2 with respect to body 1. Instantaneous center of body 2 with respect to body 1. Instantaneous center of body 2 with respect to body 1. Is that point on body 2? Is that point on body 2? Is that point on body 2? Which has zero relative velocity? Which has zero relative velocity with respect to a coincident point? With respect to a coincident point on body 1, which has zero relative velocity with respect to a coincident point on body 1. That is the common eye center, okay? The common eye center for two bodies is a point on one body which has zero relative velocity with respect to a coincident point on the other body, okay? The bodies can be anything. I just told it as 1 and 2. It can be any number. So I can even say like this. I told it's a point on body 2 which has zero relative velocity with respect to coincident point on body 1, right? In other words, I can say like this. It's a point on body 1 which has zero relative velocity with respect to coincident point on body 2. Because this eye center can lie anywhere, right? It can lie on body 1 or it can lie on body 2. It can lie outside both the bodies. So basically, when you extend that body and when you make the eye center fall on this body, velocity of that eye center should be exactly same when I consider on this moving object or the other object. That's important understanding, okay, which is required. So I don't know how many of you understood this statement. It's clear, right? Whenever I say common instantaneous center, velocity of that point should be exactly same, okay? Should be exactly same. Yeah, clear. Okay. Just write a note, write one statement, write a note. So basically, instantaneous center is nothing but, so whenever there is a relative motion, that relative motion may not be pure translation or pure rotation, it can be any kind of relative motion. That relative motion can be seen to be in perfect rotation with respect to one point in space. That point is called as instantaneous center. So any relative motion between two links can be seen to be in perfect rotation by standing at their respective instantaneous center. Here the relative motion is between board and this body. The relative motion between board and this body can also be seen to be in perfect rotation by standing at one point in space again. So maybe the board may also be moving. Here it's not moving, but it may be moving. Then if there is any, that whenever you come across any relative velocity, that relative velocity can be seen to be in perfect rotation by standing at the respective instantaneous center of rotation. Just write down like this. If there are n links in a mechanism, just listen here, if there are n links in a mechanism, how many eye centers you can look at? for n links, how many instantaneous centers we can look at? N minus 1. Why n minus 1? Whenever I say n links, so 1, 2, 3, 4 and so on, n number of links. You take any two links. Whenever I say two different links, what's the meaning of two different links? There is relative motion. So this is 1 and 4. When I say 1 and 4, there is some relative motion between 1 and 4. There is some relative motion between 1 and 3. There is some relative motion between 1 and 2. Or I can say 2 and 3, 2 and 4. Whatever it is, you take any combination, 2 and 10, 2 and 9, you take any combination. You pick any two links. Whenever you say there are two different links, there is relative motion between them. Whenever there is a relative motion, you can look at an instantaneous center, right? So if there are n links in a mechanism, for any combination of two links, you pick any two links, there will be relative motion. So that relative motion can be seen to be in perfect rotation, okay? If there are n links in a mechanism, so for any combination of two links, we can look at one eye center, okay? So we can have NC2 eye centers. NC2 is nothing but if there are n links in a mechanism, number of instantaneous centers possible are NC2. We can look at NC2 number of eye centers, okay? If there are n links in a mechanism, number of eye centers that are possible are NC2. You understood how to look at eye centers, right? How to look at eye centers? Okay. Let's take down this problem, try to solve this problem. Let's take down this question. Let's try to solve this question. A rod of length 1 meter is sliding in a corner as shown in the figure. At an instant when the rod makes an angle of 60 degrees with the horizontal, the downward velocity of point A is 1 meter per second. What's the angular velocity of this rod at this instant? So whenever they ask you to find out angular velocities of links, you have to look at center of rotation, okay? So center of rotation is instantaneous center of rotation. If you know center of rotation, then we have seen some properties for centers or rotational motions. They are applicable here, okay? Yeah, what's the answer for this? Just look at this question. He's saying that there is a rod sliding in the corner of a wall, okay? So there is a rod sliding in the corner of the wall like this. This is a rod. This rod is sliding in the corner of a wall. So this is A and this is B. And he's saying the velocity of point A is downwards. Velocity of point A is downwards. It's given in the question. Okay. The downward velocity of point A is 1 meter per second. It's sliding in the sense either it can be sliding like this, goes up and this gets in. Either this will be sliding down and this will be moving. If this is sliding down like this, so I can say velocity of point B will be in this direction. Okay. So we can easily draw. Yes. Yeah. So if you look at the question, he is saying that there is a rod sliding in the corner of a wall. So it's something like this. Yeah, a rod is sliding in the corner of a wall like this. So he's saying that velocity of point A is downwards. Velocity of point A is downwards. If this point is sliding downwards, I can easily say that this point is moving in this direction. So it's difficult to determine what direction of velocities at different other points. So other points are translating as well as rotating, okay? But these 2 points, I can say if this point is sliding down, this point has to slide to right. So we have plotted 2 velocity vectors. Once you plot 2 velocity vectors, you draw perpendiculars to the velocity vectors. You draw perpendiculars to the velocity vectors. I am drawing perpendicular to the velocity vector here. I am drawing perpendicular to the velocity vector here. So wherever the 2 perpendiculars meet, that gives an instantaneous center. So at this instant, this rod is rotating about this point, okay? This rod is rotating about this point. So it is rotating about this point with some angular velocity, omega. We can say omega. So he gave velocity of point A is 1 meter per second, okay? Velocity of point A is 1 meter per second. So if this is center of rotation, and if you want to find the velocity of point A, I told you, right? So r times omega. What is r? Ia. So velocity of point A is r times omega. R is the distance from center of rotation. Center of rotation is I. The distance from center of rotation to point A into omega. This is given as 1 meter per second. So what is Ia? Try to find out Ia, you can find out omega. So he gave this is 60 degrees, okay? He gave this angle is 60 degrees. If this is 60 degrees, try to find out this distance, okay? If this is 60, I can say this is 30 degrees. If this is 30, this length is rod of length 1 meter. This length is 1 meter. This length is 1 meter. So you can find out this distance. Sine 30 is AI divided by 1. So AI is 1 by 2. So this distance is 1 by 2. So from here you can say omega is 2 radian per second. 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 This is how you have to answer questions. Okay? So find velocity of point B in this case. Find velocity of point B in this question. Find velocity of point B in this question. Find velocity of point B in this question. So this is center of rotation, okay? If you want to find the velocity of point B, so velocity of point B is r times omega. R is distance between these 2 points, IB times omega. Okay? So velocity of point B is, so IB times R times omega. So try to find out IB. What is IB? So this is IB. How to find this IB? So this is 30. So I'm saying like this, cos 30 is, so IB divided by 1. IB is root 3 by 2. So this is root 3 by 2 and this is omega. Omega is 2. So velocity of point B is root 3 meter per second. 1.71. It's root 3 meter per second. Okay. So basically, if you look at center of rotation, you can find out velocity of any point. Okay. If someone asks you to find out velocity of point C, how to find velocity of point C? Midpoint. What you do is you find this distance. Okay. Velocity of point C is so IC times omega. You can find out velocity of any point. Okay. You can find out velocity of any point on the rod. You know center of rotation of the rod. You know angular velocity of the rod. So you can find out velocity of any point on the rod by just calculating the distance of that particular point from the center. Okay. So there is a rod. This rod is in general plane motion. Okay. This is neither in pure translation nor in pure rotation. This rod is in general plane motion. Okay. This rod is in general plane motion, so I'm making this rod less inclined. Okay. This angle is 20 degrees. I'm calling this as P and this is Q. This is the direction of velocity of point P. This is velocity of point Q. This angle is 45 degrees. This angle is 45 degrees. So length of this limb I am assuming is 2 meters, okay? Length of this rod, it's a rigid rod, okay? So this method of locating instantaneous centers is applicable only for rigid links, okay? It's not applicable for flexible links. It's only for rigid links. Solve this problem. Find velocity of point Q at this instant. Find velocity of point Q. Find velocity of point Q and angular velocity of the link at this instant. Find velocity of point Q. Find velocity of point Q and angular velocity of the link at this instant. At this instant. Right now, directions of velocities at P and Q are given. Directions of velocities at P and Q are given. And magnitude of velocity at P is given. Magnitude of velocity at P is given. So directions of velocities at P and Q are given in the question. And magnitude of velocity at P is given in the question. You look at instantaneous center of rotation. And at the same time, you try to find out angular velocity of the link, and you try to find out a velocity of point Q. So whenever I say velocity of a link, so I mean angular velocity of the link. Okay? So if I talk about a point, I have to specify a point. Okay? So on a link, there are infinite number of points. So which point velocity? I will be specific when I talk about points. So point on. So velocity of point P on the link is 1 meter per second and its direction is this one. Velocity of point Q is in this direction, but I don't know the magnitude. You try to find out the magnitude of velocity of point Q and the direction of, angular velocity of this link. Try to find out angular velocity of the link and velocity of Q. This is a GATE question, okay? It was asked for 2 marks. So how to solve this problem? Try to look at the instantaneous centers. So I'm looking at the instantaneous center. You draw a line perpendicular to the velocity vector. So both the velocity vectors are given in the question. This is the line perpendicular to the velocity vector. And here the line perpendicular to the velocity vector is like this. So these two lines are meeting here, okay? This is instantaneous center of rotation. So at this instant I say this is rotating in this direction. At this instant, so these two are perpendicular, okay? This is 90 degrees. This is 90 degrees. This is 90 degrees. This is I. You give velocity of point P. So I am assuming this link is rotating in this direction with an angular velocity omega. So velocity of point P I can write like this. So it is R times omega. So R is the distance between I and P. So R times omega. So velocity of point P is known to us. This is 1 meter per second. If you can find the distance IP, you can find out omega, okay? Try to find out this distance IP. If you give length of the link as 2 meters. If this is 20, so I can say this is 70 degrees, okay? This is 70 degrees. Try to find out this angle. So this is 90 degrees, okay? This is a horizontal line. So this total angle, you can see this is 180 degrees, okay? This is already 45 degrees. This is 90 degrees. So I can say this total angle should be 180 degrees. I can say it's a straight line, okay? So this will be 45 degrees. So this is 90 degrees. 90, 70. So what will be this? This is, I think, 20 degrees. This will be 20 degrees. So 180 degrees. That is 20. This total angle is 65 degrees, okay? This total angle is 65 degrees. This is 65 degrees. So if this is 70, this is 65. So this angle is 45 degrees. This is 45. Okay. So these are the different angles. So I want to find out IP distance, okay? So I can write the sine rule for this. So this side IP. So IP divided by sine of 65 is same as IQ divided by sine 70. Sine 70 is 2 meters divided by the opposite angle, sine of opposite angle, sine 45. So if you want to find out IP is sine 65 divided by sine 45. This is IP. So from here you can find out omega. So omega is 1 by IP. What is IP? This is sine 45 divided by sine 65. If I simplify this, you will get omega. So I forgot to correct that. Let's listen here. So first, he gave the velocity vectors inside the question. He gave velocity vectors in the question. So you can look at the instantaneous center. So this is a horizontal line. You draw perpendiculars to the velocity vectors. I have drawn a perpendicular to the velocity vector here. I have drawn a perpendicular to the velocity vector here. So where are the two perpendiculars meet, that gives you the instantaneous center of rotation. So depending on the direction of velocity vectors, I am assuming this link is rotating about this point in this direction with an angular velocity omega. Okay. So in the question he gave velocity of point P, he is asking us to find out velocity of point Q and angular velocity of the link. So velocity of point P I can write like this. Velocity of point P is r times omega. This is center of rotation. Okay. So this is center of rotation. Radius is the distance between these 2 points. So r is IP. R times angular velocity of the link. So if I can find this distance IP, we can solve the problem. Okay. So how to find this IP? So this is 20 degrees. This is 70 degrees. Okay. This is 70 degrees. And I am drawing a triangle here. This is 90 degrees. This is 90, this is 70. So this is 90 and this is 70. I can say this is 20 degrees. This is 20 degrees. And if you look at this one, this is already 45 degrees. This is 45 degrees. This is 90. This is a straight line, right? The straight line, it should be 180 degrees. So I can say this will be 45 degrees. This is 45, this is 45, 90 and plus 90, 180 degrees. So this is 180 degrees. So this is 90, okay? And if you look at this one, this total angle is 65 degrees, okay? This total angle is 65 degrees. This is 70 degrees, this is 65 degrees. So I can say this will be 45 degrees, okay? 45 degrees. So I'm writing sine rule for this triangle. If I write sine rule, so I want to find IP. So IP divided by sine of opposite angle. Opposite angle is 65 degrees. So similarly I can write like this, IQ divided by opposite angle is 70 degrees. And 2 meters opposite angle is 45 degrees, sine 45. So from here I want to find out IP, okay? So IP is 2 into sine 65 divided by sine 45. This is IP. So velocity of point P is IP times omega, okay? Velocity of point P is IP times omega. IP times omega. Velocity of point P is given in the question. This is 1 meter per second. So we know this IP. IP is 2 into sine 65 divided by sine 45 into omega. So from here you can find it omega. Sine 45 by 2 sine 65. What is this? What is omega? Angular velocity of the link. What is angular velocity of the link? 0.39. Angular velocity of the link is 0.39 radian per second. Okay. This is angular velocity of the link. This is angular velocity of the link. So try to find out velocity of point Q. So velocity of point Q is r times omega. Okay. This is center of rotation. Radius is this distance. This is the radius multiplied by omega. Velocity of point Q is distance of Q from center of rotation times omega. So velocity of point Q we need to find out. So what is IQ? IQ I am writing like this. 2 sine 70 divided by sine 45. into omega, we already found this. What is this? .03 meter per second. Okay. So you understood how to look at icenters, right? Everyone understood how to look at icenters, right? And how to solve problems by using icenters. Is this clear? Yeah. Just go back to degrees of freedom. I forgot to discuss one thing. Go back to degrees of freedom. In degrees of freedom, we have seen the formula. We calculate degrees of freedom by using this formula. Kurzbach's criterion. This is 3 into n minus 1 minus 2 times lower minus higher. Okay. This is Kurzbach's criterion. Okay. This Kurzbach's criterion is valid only when I can say what is number of links here. Number of links, number of lower pace, number of higher pace. These are all rigid links. Okay. These are rigid links. How the rigid links are connected. Okay. So whenever there is any flexible link, you have to replace that flexible link with a rigid link, and then you have to solve the problem. Okay. So sometimes you may encounter a spring kind of arrangement. So whenever you come across any spring arrangements inside the mechanism, so you replace that spring with two links like this. So what is the basic purpose of a spring? So I can increase the distance between these 2 points or decrease the distance between these 2 points. So this can be achieved with the help of these two links. Okay. These two links connected with the turning pair is same as spring work. Okay. The distance between these 2 points can be increased or decreased. Just like the spring, it can be increased or decreased. So whenever you come across any spring inside your mechanism, you have to replace that spring with the help of two links connected by turning pair. In SS there are some good questions of degrees of freedom. Try to practice them. In GATE, there are no good questions from degrees of freedom. Okay. So very few questions are there, and we discuss them. Let's go through SS Ratan. So tomorrow we'll continue with this velocity analysis. Velocity analysis is very important for GATE. I hope you understood this discussion. We'll meet in the next class. Do you have any doubts?